Hello everyone, welcome to Coffee with Caleffi. My name is Max Rohr and I am going to be the host today. So I'm going to walk through the presentation and go over what we're doing next month as well. So I'll go through a couple quick housekeeping slides here and we'll get started. If you have any questions throughout the webinar, go ahead and type those into the questions pane and I'll keep an eye on that. We're a little short staffed today, so I may not get to all the questions as we go through the webinar, but I'll do my best at the end to catch up with those. So with that said, let me go through the next couple housekeeping slides. If you're having issues with audio, just log out and log back in is probably the best advice. I don't know how long it would take to get through the tech support phone number, so that's probably the best path forward there. If you want a copy of the presentation, I saved this as a PDF just a few minutes ago, so you can hit yes in the post-webinar survey and get a download of that. And then also we'll put this up on YouTube as well. If you're looking for a certificate of attendance, if this works for your jurisdiction, we will provide this as well. So that'll be emails to the attendees after the event is over. This topic today is really from Hydronics 34. So this is our latest edition of Hydronics. This is something that's available online now. And May 7th, I believe, is the date that they're going to ship out to people that have signed up for hard copies. There's also a link in the chat if you want to sign up for a hard copy and get on the list for future issues, or even to just see the full archive of all the digital editions there. And this is the website to go directly there, but I've also got it in the chat. Next month, we're going to be talking about balancing, but plumbing balancing. So this is going to be another one that focuses on thermal balancing technology, not hydronics, which is what we're doing today. So this is, I have the pleasure of introducing myself today because we're a little short-staffed. Everybody's out in the field training. So what I'm going to do is talk about hydronic balancing and how it's changed over the years and kind of the modern technology we have available. There is no perfect answer for a specific balancing valve technology that will work for everything. It depends on the project criteria. It depends on a lot of different things that I'll cover. So I'll go through kind of how you would evaluate how that works, and that's really the spirit of what Hydronics 34 is, to just give you some background for making the decision if this is the right balancing valve for the project. Okay, here is our plan for today. So we're going to talk about fundamentals. We're going to go through some system goals and how to meet them, how to commission a system. I've got a poll that'll be interesting along those lines. And then how do we keep these things running well? One of the tricky things about a balancing valve is for it to work and effectively maintain the flow of the system fluid through the different terminal units or whatever the case may be. There's a small orifice involved in these valves. This is something that's really close to the terminal unit. We don't have some 4-inch opening going through a balancing valve that would be easy for debris to pass through. So we need to keep the system really clean if we have a lot of balancing valves in the system, and I'll discuss the ways to do that. So if you are, again, looking for DHW balancing, I'm not going to cover that today specifically for thermal balancing valves, but come back next month. So we've got that link in the chat as well. And Cody and Kevin from our team are going to be going into a lot of detail just on thermal balancing valves for plumbing systems. But today, we're going to talk about hydronics. So one of the things that hydronic heating systems may need would be a balancing valve in different parts of the building. So I've circled a couple examples here. This can get really complicated really fast. Maybe in a residential installation where we have some sort of radiators that are simple. Maybe we don't have balancing valves everywhere. Maybe we just have zone valves or something like that. And that's kind of the technology required for the task at hand. In a commercial project, we might have a lot of balancing valves. We might have a lot of balancing valves in series. This might be a balancing valve here going to a radiant manifold that has its own set of 5 sub-balancing points there. So that can be a very complex thing to work through in a hydronic system. We'll go through some of the steps to make this easier, or some of the technology that could take this task and iron out the details a little bit better, because there's, again, as I said, no perfect answer here. So what I wanted to start with, since this is kind of a fundamentals level hydronic balancing piece at the beginning here is an analogy as it relates to a track. This is one of the things that I try and use to explain the task at hand for hydronic balancing as it relates to a track and field track. So let's say I'm going to race Cody Mack. He's one of the other trainers at Caleffi. I challenge him to a race around this track, just like you'd see at a high school or something like that. I decide that it would be great if I take the inside lane. He's going to take the outside lane. You may not know this about Cody and I. We run at exactly the same speed for the sake of the analogy. So we are going to start running at the same time when the starting gun goes off. This is probably what will happen. I'm going to cross the finish line a little bit ahead of Cody because he's got a longer path around the track. He is in an outer lane. He's got an unequal distance to what I have to cross the finish line. I'm going to get back to the start line, the finish line, sooner than Cody will if we're running the exact same speed. So what can we do here? In track and field, they stagger the start line. So for a 400-meter race or something like that, I might start here, Cody might start here. We're going to start at the same time, and that's going to equal out the distance. So if we're running at exactly the same speed, we're going to tie. Here's where that comes into a hydronic system. So in a hydronic system, we need all of these circuits. So we'll say each one of these circuits is a runner. We'll say that the panel radiator, the fan coil, and then the whatever this is, the terminal unit, some sort of ceiling cassette or whatever. Let's say all of those are the runners. We need them to all come back to the start line at the same time because these are circulated loops. These aren't, an open pumped system where they can start and stop, and who knows what part of the grass is going to get water through a sprinkler system or something like that. These are hydronic loops that are all coming back to the start line, in the analogy being the circulator. So this is the start line, and we need to get the water back to the finish line in different delta T's for these different heat emitters, but we don't have the option to do unequal starting lines, essentially. We need this to be a circuit that comes all the way back to the same start and finish line. So in that way, here's kind of what we're doing to a track that you would see at a high school. We are all circulating. So we're going to have a pump that's going to bring us around the track. We're going to take a balancing valve in a hydronic application to add some resistance to this innermost lane. We may or may not be able to make these lanes equidistant, just based on building considerations, based on the ability to do a perfect reverse return ladder that I can show a little bit later. We may not have that option. That's where balancing valves come in, that if this is the first riser to go up to some fan coils, we could either just put a bunch of extra pipe in the chase to make it longer and waste some materials and have additional heat loss there that's going to kind of fight what we're trying to do, or we could add a little bit of resistance to the path of least resistance here and try and equal those things out. That's what we're adjusting with a hydronic balancing valve, and that's how we get the runners to cross the start line and the finish line at the same time. So what is the path of least resistance in a hydronic system? I'm going to get a pen out here so I can make a couple marks here. So if we didn't use any balancing valves, we'll just say there are no balancing valves in the system, and we turn on the circulator, what's going to happen is we're going to get a lot of flow to go through this first branch. That's the path of least resistance. That's the shortest way around the track to get back to the start line. It would take a runner a very long time to go all the way to the most hydraulically remote path through this system. That's going to be an issue because if you lived in this unit, you might not get heat very well through the building. We need to kind of balance this out. There are some tricks that we can play here, and as far as the installation goes, that we could taper the pipe diameter going down this line to save the cost on materials. We don't need to have, we'll say this is 2-inch pipe to start with. We don't need 2-inch pipe all the way to the end. But this kind of hurts us in the sense that these are going to be even more out of balance compared to doing a reverse return. Let's see if I can draw this straight enough to come back around and then maybe connect here. That might take us to more of an equal ladder for the pressure drop across these different parts of the building. It's a lot more material, and we may never be able to get it perfect. maybe in something like turf conditioning for what they use for sports fields for the NFL and for Major League Soccer and things like that, where they're actually using radiant heating like it's snow melt, but just to keep the root bed warm. That's an enormous rectangle. We might get a pretty good reverse return setup there to take the pipe across the field. In a building, in a multi-story building, it's going to be harder to do that every time. So that's where the balancing valves come in to kind of equal out the length of the track as we go around. So now what we're doing is trying to adjust this non-equal, we'll say some of these are actually a little bit longer than the others. There's more pipe here. Maybe this one goes a completely different path and has more heat emitters than we planned on or something like that. That's realistic in a building. That happens all the time. How do we get that back to an equal length for the track all the way around? Here's what we can do. We can add some resistance to these mains, to these laterals, to the crosses here as we go down the line here. So without doing a reverse return piping, we could just adjust this balancing valve so more pressure is required to go through this first loop than the one at the end. Maybe the one at the end is fully open. Some people will say, well, why do you even need one at the end? I always like having one at the end because you never know what happens in the future. Maybe we add another couple zones here and then we would forget that we have to chop in a balancing valve there. So it could be wide open, but it's never a bad idea to have a balancing valve on all of these. Again, we're also assuming this is the path of most resistance. It could be that this one has 50 more 90s than we had planned to work around a bunch of different things in the building. And this could actually be the one that needs to be wide open, and this one may have to bounce down a little bit. So with a balancing valve, what we're doing is we're kind of manufacturing a little bit more of a pressure drop across the path of least resistance to iron everything out. So pretty simple concept here, but it gets a lot more complicated really quickly. So one of the things that we have to figure out is how we size the circulator to overcome the pressure drop of the branches, what they actually are. That's one of the things that's a little tricky, is that when we look at a diagram like this is a theoretical building that will never look exactly like this. We're never going to get all of these crosses exactly the same length. This is going to be more of a laboratory condition type scenario. So what we need is a circulator that can overcome the pressure drop of the branch, everything that's in here. It might be a zone valve, the heat emitters, whatever the case may be, plus the balancing valve that we're using to kind of modify the path of least resistance to equal it out across the building, plus this delta P excess. So this is what we are going to have available from the circulator that's just a little bit more than what we need to overcome the pressure drop through all these valves. That gives us the ability to tune them a little bit. This is really important, this delta P excess. I'm going to go through that in the next slide here. So delta P excess could be enormous if instead of a properly sized 1 horsepower circulator, in this example, if we had a 5 horsepower circulator here, we are going to have an abundance of delta P excess, and that's not good. We don't want that. And here's why. So we have a regular, I don't know if he's on today, Drew Gillette comes to a lot of these Coffee with Caleffi webinars. He's an engineer, and he typed into a webinar at one point, all balancing is wasting pump energy. How do you balance without valves or energy waste? So another way to say that is all balancing is parasitic. That is a true statement. Ideally, we don't have to add resistance that's going to increase our electrical consumption to iron out the different crosses in this diagram. However, in the real world, if we can't get these perfectly balanced as far as without a balancing valve, as far as just the pressure drop across these different crosses here, we need balancing valves to help fix it. And that's one of the things that if we could build a building perfectly straight and not have any sort of other trades in the building that we have to work around, and we could maybe do a reverse return here, theoretically in lab conditions, we wouldn't need balancing valves. In a radiant heating manifold, maybe we're close with that. Maybe if we have exactly 333-foot loops through a manifold, we don't need to bounce that at all. So we don't need any sub-balancing there. But to get to that manifold on the 15th floor or something like that, that's where we might need some balancing valves to even that out a little bit. So to Drew's point, this delta P excess is super important. We want to minimize this to the absolute, just a half of a PSI of delta P excess would be fantastic. It's Earth Day week this week, and one of the things that we were looking at in the marketing department as I was trying to figure out, should I put together an Earth Day post? I'm very sensitive to greenwashing along those lines, that if we have something that isn't providing substance and it's just extra electricity to post something on social media to say Happy Earth Day, what value did we add there? And then I thought about it in the context of this webinar. This is the biggest value that people on this call can provide on Earth Day, is to pay attention to this delta P excess. This is significant. This is something that we can do to really make people comfortable in their spaces, maybe even more comfortable if they have hot and cold zones in an unbalanced building, and save an enormous amount of energy. That this energy waste, all balancing valves are parasitic. Yep, we need to minimize the amount of balancing that we need to do, and I'll go through some of those sizing criteria. Realistically, we might need them to iron out the hot and cold spaces in a building and get back to the design intent for these different heat emitters, but we really need to minimize this delta P excess to avoid energy waste and to increase comfort. The good news is we can do it, and I'm going to go through the different examples of how as we go through the presentation here, because if we can't pipe these with equal pressure drop, we're in trouble. I want to give a shout out to Concept Mechanical in Avon, Colorado. I think I've said this on Coffee with Caleffi before. They were a mechanical contractor I used to work with when I was a manufacturer's rep. And I was asking them at one point, I sold pumps at the time, I was asking them, what pumps do you have on this project? And they said, we don't know yet. And I was like, that seems weird, because you're halfway done with the construction of the building. Most of the time you would have that on the schedule already. But they had engineering in-house. They had a guy that would go through all of the sizing, and then the guy sitting next to him would go out to the job site and make sure that the team installed it that way. But what he said is, we don't know the pump sizing yet, because we actually wait till we pipe everything, and then we go back in and we count the fittings and figure out what the as-built actually are. That's the only way we're going to be able to size the pump properly. I would say that ECM circulators have made that margin of error a little bit wider, that we could probably put in a delta P circulator, an ECM technology circulator, and be close enough most times. But I really liked that answer, because that's the way to reduce the delta P excess. If we somehow were able to install that system, and instead of using kind of a factor of fittings that we would use to size a circulator, just as a rule of thumb type example, if we went through and actually found the pressure drop through all of these, we could get that pump sizing really on the nail, and that would be fantastic, and we could just have a minimum delta P excess there. So that's kind of the big picture problem that we can help solve with balancing valves, and I'll go through how we can minimize the amount of energy that we need to do this balancing task. So I've got probably the most scientific poll that I've ever put together here for the crowd. I'm going to launch this and then wait about 40 seconds and see what your answers are here. This is something that I am very interested for the designers on the call to answer. As far as a balancing report goes, how do you feel about them? Is it something that I do a lot of these presentations for individual engineering firms, and I'll ask about balancing reports, and I get a wide variety of answers. I get absolutely, I require them, but we didn't look at the last one because it went well, or I don't require them, they're not required by my state. And then my favorite one is, what is a balancing report? Seems boring, not interested. We either select valves that are going to help us with this task, or it just doesn't come up. We're not going to get into those details. So let me close this and see. I'll share this with the group. Oh, it looks like a couple people are still answering here. Okay, so good news. It looks like we've got a pretty close race for both of the I require them options. So that's fantastic. I don't require them is a hard one because we don't know how close to the design intent we got there. I'm really happy to see this. Maybe we just have kind of a skewed audience that you're taking the time to take an hour to learn about balancing here. You're probably not the people that don't require the balancing valves compared to the general population here. So this is really good news that I require them and double check them. I'll go through a couple ways to verify balancing valves that for designers is easier than getting your own manometer and going to every single one of these. But this is something that's really important to make sure that we're not wasting energy and that we're not creating hot and cold spots throughout the building. Okay, let's go through the next couple pieces that are related to some just key sizing things for balancing valves. So one of them that I literally look up every single time I talk about valve authority, because it is a little bit of a complex concept, the ability of a manual balancing valve, which I'll cover first in our next set of discussions through the different product types, through a manual balancing valve to regulate the branch flow rate depends on the pressure drop across the valve relative to the pressure drop across the entire branch. So this is what we're talking about here in this pressure drop for the total main. What share of that pressure drop is the balancing valve? Is it something that is a very small percentage, or is it about 50%? So our recommendation for valve authority is, and I'll go into this in a little bit more detail in the next slides as well, is to select a valve that has about 50% of the total pressure drop across the branch. So I'll show some examples there, but that's a good thing to shoot for, or else we don't have the controllability that we're looking for. Really, if you think of it as like the resolution that you would have, or maybe the ability to steer an enormous truck with a tiny steering wheel, that we have to be almost completely closed to figure that out. This is important because we need to, going back to that concept mechanical example, we need to know the pressure drop of the main outside of the balancing valve to size the balancing valve. And if that's kind of conceptual based on a set of plans where everything's a straight line, we may not have 100% of the information we need to really nail that balancing valve sizing. We may be close enough if we just selected a 3/4 inch manual balancing valve for a 3/4 inch line with fin tube baseboard. That might be close enough, but it's not the way to really get the adjustability and minimize the energy consumption of this task. So here's the reason we want to have that valve authority figured out, is because most balancing valves, even a globe valve that's going to have a better kind of characterized plug that I'll show a little bit later in some examples that are back to Hydronics 8, which was kind of the first time we talked about balancing at Caleffi in one of those journals. It's not proportional here. So when the valve stem has reached 50% open, we are actually 90% closed here. And that's one of the things that I think is really difficult in the field, that without a balancing report, sometimes we suspect, and we've heard from some installers as well, is they'll start with the balancing valves closed to 50% and see if that does it. But they're thinking that 50% is 50% of the flow, and it is not. So if you close this balancing valve 50%, we're at 90% closed. That might mean that we need more pump to overcome that pressure drop, and that might be the reason that in the field, a service contractor is like, I don't think we have the right pump here, and we're getting not enough flow out to these zones, and it may be because all of the balancing valves are 90% closed, and we don't want that. We don't want to upsize the pump because the valve is too far closed, but this is all kind of related to the valve authority, and we can select different valves and different disc types that cover the orifice to help with this scenario as well. I'll go through a couple of examples there. So big picture, an oversized valve will have a lower pressure drop, but it might need to be almost completely closed to have any sort of adjustability, and you might be down to like 99% closed versus 98% closed is required to have any effect on the flow through that lateral. We don't want that. On the other side of the equation, we don't want a really undersized valve, because then we might need more pump to go through that really high pressure drop of the valve and waste energy to do that task. So There's no perfect answer for what the in-between is for an oversized and undersized valve, but that 50% valve authority is going to be a good place to start there. We go through these calculations in Hydronics 8 in a lot more detail, and you can get to that through that link that's in the chat. We go through in many pages these valve authority, flow coefficient considerations with a lot of different examples here. So a couple things to point out with the C sub V calculation here that's easy to overlook in hydronics. The default here, if you're using some sort of calculator, is probably 60 Fahrenheit density pure water. We may not have that in a lot of cases if it's glycol at 140 degrees Fahrenheit or something like that. So that's something to pay attention to there that can affect the calculations. Maybe not drastically, but we want to make sure that we get it right, and that's an easy one to overlook in the C sub V calculation. So now I'm going to take a quick look at the chat and see if there's anything that's helpful. One of the comments is that's why we have constant pressure circulators now. That's an excellent point, and I'm going to show you where that can really help with manual balancing valves in just a couple slides here. So this slide apparently. So a manual balancing valve is the original, most common, most copied, most widely available type of balancing valve for a hydronic system. Again, they will work. A manual balancing valve will work. I would say that it's the most labor intensive by a pretty big factor compared to the other valves that I'm going to show you here. So one of the things that's tricky about a manual balancing valve is as the different zones open and close, the pressure changes through these valves and it throws your chart off. It puts you on a different point in that chart depending on the pressure across this valve. Any of these three valves, kind of this variable orifice, fixed orifice with the venturi right here, or this quick setter product that we make that actually has flow meter built into it. So when you pull this pin, it'll go through the flow meter, so you don't need an extra tool. And this is a really cool one for commissioning engineers or people that are trying to baseline maybe like a 100-year-old building with no as-built to figure out, do we even have flow to this part of the building right now? You could go in and just pull this pin and see if the flow rate is what you're looking for and adjust this ball valve to throttle it back down if you needed to without having to have a tool. So this is kind of a cool troubleshooting valve. We used to use these a lot as well in like geo loop fields to make the balancing task easy. One of the things that, as was pointed out in the comments, delta P circulators, ECM circulators, are really helpful in this scenario with manual balancing valves now. So the good news is, in the past with a single speed circulator, as the flow rate went up, you were landing somewhere else on the curve. If you had all 10 zones open in a building with a fixed speed pump, the pressure was very different from when 5 of those zones close or all but 2 of the zones close or something like that. The delta P circulators that are able to hold a constant pressure, which is a setting that most of the ECM circulators have now, can be really helpful there because they could be 10 GPM or they could be 40 GPM, but at the same pressure. That's going to make the task of balancing a manual valve really easier, because what we're planning for with a single speed pump and manual balancing valves is worst case scenario, and then we're going to be off all of the other times. And I'll show you an example of that we would be overflow if a single zone started to close. My biggest question here is somebody's actually going to balance these things, right? That a balancing valve, a manual just twisted 50% closed isn't going to do it. That's not going to help us, and we're going to end up oversizing the pump, or the ECM pump is going to have to spin harder and use more electricity to overcome the valves that are too far closed. So the next technology that we'll talk about would be an automatic balancing valve. This is reactive to the pressure, but it's going to maintain a flow rate independent of the pressure developed. So this is a cool valve because you select it with a specific GPM in mind. So you say, I want 1 GPM through this hydronic fan coil, and it's going to maintain that flow rate as the pressure increases and decreases. So these are really accurate, within 10% plus or minus of the flow rating. And one of the major advantages here is they don't need to be commissioned. You don't need a balancing contractor to do this necessarily. There are some states, like Oregon is one of them, where they want to have a separate trade, not the installing contractor come in and verify that we do have 1 GPM through that fan coil. So look for products that have the pressure ports here. This is, I usually say, is going to be a very boring job. If you have 100 automatic balancing valves in a job and you do a commissioning report, you're going to probably see 99 of those valves that are at like plus or minus of a maximum of 10% of that 1 GPM. So that's going to be a really boring job to go through that building. If a balancing contractor or report is not required, a just straight through compact version of the automatic balancing valve is going to save a little bit of brass and a little bit of time there. You can still, these are domestic hot water examples that have a temperature gauge. You can get a temperature gauge or not, depending on the project goals. But a big thing here is no balancing labor is required to get these valves installed and make sure that we've got the right flow rate to each of the different parts of the building, as long as you get them pointed in the right direction, which comes up sometimes. You have to make sure that that arrow is pointing in the right direction, which unfortunately is something that is missed occasionally, and we get those calls to tech support. So how does it work? Automatic balancing valve is pretty simple. We've got a spring inside here with this little cartridge that you can see a little bit better from this cutaway. This cartridge has kind of a half of an hourglass shape right here, that as the pressure increases, so we'll say that the pressure of the circulator, all the zones are open, so the pressure across this particular riser or something like that is pretty low. The orifice is going to be a bigger size. So basically everything you can see here highlighted in red is going to be wide open. Now let's say that 9 of the other 10 zones in the building start to close. In that scenario, the pressure really increases. All of that flow, all 10 lanes of traffic that used to go through all of the different parts of the building are now funneled through that one automatic balancing valve that's still open. So the pressure just went way up there. But what changes is in this calibrated orifice, the orifice size decreases. So it pushes this spring down, and then now we're just down to a little tiny bit of this cartridge that is allowing flow through. So as the pressure increases, the orifice size decreases, and that relationship is how we're able to keep the flow rate right on what we had selected. And this is something that I don't even know what the accuracy is down to the micron, down to the nanometer, that we have to kind of make sure that that orifice is the proper size as it goes through the flow range to maintain that 1 GPM with that tolerance. So here's the reason that the fixed speed circulators have been kind of tricky to balance with the manual balancing valve in the past. So if we had a 4-zone system, a simple residential system with the fixed speed circulator, all zones are on, we could tune all these balancing valves. They're iterative, so if we adjust one of these, it's going to affect the other 3, but we can do it. We can get all these balanced out. We'll say this is the target that we need for all of these different baseboard zones. You can see that the baseboard's a little bit different length, but here's the problem. When one of these zones turns off, if we're using a fixed speed circulator, we're now overflow from 4 GPM to 4.6, up to 4.5 here, up to 6.2 here, through the other zones. So a fixed speed circulator and manual balancing valves are going to work great in the scenario that the power went out for 6 hours, then we turn the building back on, the boiler comes back to life, and every single zone valve is open. It's going to work great then. It's going to have some, above flow rate potential in every other 99.9% of the year scenario, and we don't really want that. So as mentioned before, we could do a constant pressure setting for an ECM circulator, which would mean that we would always have the same pressure that we designed and commissioned the manual balancing valves for, and the flow rate would just change. So if this zone turns off, maybe we have dropped from 22 to 15.3 GPM, but the pressure of the head did not change, and that's an excellent way to apply a manual balancing valve. Here's the difference with an automatic balancing valve that makes this easier. I'm still a huge fan of ECM technology, just from an energy consumption standpoint, that it's just a really good way to go. It's one of the things that had started when I was earlier in my career is like, oh, this is really cool, this is really energy efficient, to no, this is a problem solving technology. ECM technology is really a good way to make sure buildings are installed and operating correctly outside of the energy savings. The energy savings is has been in a lot of cases a bonus, but the ability to just tune buildings well is where the ECM technology shines. So let's say we switch to automatic balancing valves here, and we preset these. We've got the cartridge selected. We're pointed in the right direction for 6, 4, 8, 4 GPM. Now, let's say zone 2 turns off. The cool thing is the fixed speed circulator slows down, but even without the ability to modulate here, we're going to maintain that for 6, 4 GPM through the other zones. So that's really useful. And for complex buildings, we can just say, hey, make sure we have a 4 GPM automatic balancing valve on that part of the building with the baseboard, and we don't really have to go back and do a lot of adjusting at all to make sure we're in good shape there. Maybe, let's say we added another 10 feet of, obviously nothing in this presentation is to scale. Let's say we added another 10 feet of fin tube baseboard here. We might have to go back and change this from a 4 GPM to a 6 GPM cartridge. So that's the disadvantage of automatic technologies. We're actually switching parts. We're actually going back and changing a cartridge there, where with the manual balancing valves, we could just readjust. So the next piece here that I want to talk about, let me just make sure I'm not missing something in the chat here. Okay, so the next thing that I wanted to cover is kind of the evolution of the balancing valves for the premium way to control flow through a building is what we would call a pressure independent control valve. And I'll go through why this is kind of the premium option here. And basically it just gives us the most controllability, because it's going to be a pressure independent control like an automatic balancing valve, but we can add this additional feature that it can contain its own zone valve basically. So we could have an on-off control with a little thermal motor here. That's a simple way to say we do not want flow through fan coil number 2 right now. We're going to turn that off without using a separate device. The most premium, the super platinum premium Delta Sky Mile option for a zone would be a proportional control on top of an automatic balancing valve, essentially. That's what we're doing with this PIC valve. So we could we could establish it so it has a maximum flow rate of 1 GPM, but then we could also, from a building management system, send it a signal and modulate how much flow we need through that fan coil in this example. That is the best energy efficient option, that we're actually varying the flow rate beyond establishing that maximum speed limit. And then we also have some cool capabilities to do fail in place or fail open, fail close. These are only 2 of the 4 different actuators that we offer, and there are a million different choices here, and also gives them a lot of flexibility to the integrators to figure out, when do we need 1 volt, when do we need 10, what does that mean, how do we adjust the flow rate here based on the building and the sensors that we have for occupant comfort. So here's how we can kind of break this down a little bit more. If we were looking at a zone valve and a manual balancing valve for a terminal unit, absolutely, again, will work. We're going to need 2 different devices there, or an automatic balancing valve and a zone valve. We need 2 there. The PIC valve can really just be 1 valve to do all of these tasks, that hooks to not just an on-off signal from a zone valve, from a thermostat, but to some sort of modulating signal, which is even better. So we've got the proportional control there. The easy selection part of it, I guess this is a little bit subjective, but easy to select a manual balancing valve, a little bit harder than just saying I want a 1 GPM cartridge here, or I want a PIC valve with a maximum of a 1 GPM, flow number there that we can actually set, but I'll show you that a little bit later as well. The adjustable presetting, nope, can't do that with a manual. Yes, very easy with an automatic balancing valve, and then yes, we can pre-select which flow orifice basically we want that automatic balancing pressure independent cartridge, and then have some flexibility within that. So easy to calibrate, harder with the manual balancing valves. Could take a long time to get through a building like that, where the automatic and the PIC valve are going to be easier to do if we made the selection correctly to start with. So here's the big piece of this, that even as I look at balancing valves in our own catalog, sometimes I think, okay, well, is this good enough? Is a zone valve and automatic balancing valve with an ECM circulator energy efficiency wise, is that good enough? Maybe. So that is the case maybe for a set of townhomes or some sort of smaller construction like commercial project. That might mean we don't need a building automation system at all to control the HVAC. We've just got a simple thermostat that's giving us a signal there. However, and I'll show a couple case study examples, if we get into some like 60-story building, plus or minus 5% accuracy that we can really dial in with the PIC valve could be an enormous win there from an energy efficiency standpoint. That could be hundreds of thousands of dollars worth of energy a year for whoever pays the bills, whatever stakeholders we have there. And we can just really dial in that temperature in a space that may be very sensitive, like a hotel or something like that, so we don't have big temperature swings there. That's where the PIC valve is going to be the most premium way to deliver just the perfect amount of BTUs to match the heat loss in a space all the time. That's the best way to do it. And I'll kind of cover maybe some examples where you could get to a breaking point between those two. If you've got building automation already for the climate control pieces, that if you're using that for air changes and CO2 control and things like that, those are the places that a PIC valve is naturally going to be a better fit than putting a building management system into a light commercial project just to do the PIC valves. Probably going to be expensive. That might not be the best way to go, but it depends. So the evolution of hydronic balancing is really a move in this direction from manual to automatic to a PIC valve style for that most energy efficient, most comfortable version of control into a space. You can again use any of these, and depending on who's paying the bill, if the person who is in charge of the budget for balancing is looking at purchase price, this is the, I don't know what shape I'm drawing here. This is the, I'll do a check mark instead, the valve to use. Purchase price is going to be lowest. No building management system to tie in or anything like that. However, if you can't find a balancing contractor that's going to work for $10 an hour, you may be paying way more for a manual balancing valve to be fully commissioned and adjusted and perfect compared to an automatic balancing valve that we can just select the cartridge. This is a good kind of profile of what that shape looks like. Select that, install that, and not have to commission. And then the most premium energy efficiency temperature control would be with the PIC valve. And also we can pre-select that so we're in the ballpark with the flow rate that we want just based on the product order. So let's say we're trying to go that additional step. We've decided that a PIC valve might be a good fit for a project. And let's say this project has fan coils or some sort of terminal unit that we need to assemble a bigger kit where we've got the PIC valve, a drain for installation, flow meter, insulation jacket, ball valve to do a bypass if we want to do that service, and then isolate the system from the fan coil if we ever needed to change that or do if we had a leak or something weird happen there, plus a drain for a strainer and a drain to get any debris that may have made its way all the way up here. So this is the traditional way to do this. This is 20 field connections to put this together with a fan coil terminal unit. One of the cool things about the PIC valve is that we can really incorporate a lot of componentry into a smaller envelope. So this is a fan coil kit with a PIC valve that now is just 4 field connections. And these could be flex hoses, or you could hard pipe these or whatever's useful for your project. But there's a lot of functionality built into these kits that makes this task easier and smaller and lighter, and just is a big win in a lot of cases with the insulation jacket that is going to leave the actuator exposed. We don't really want to completely cover an actuator with insulation because it's going to get too hot. We want that to be able to breathe a little bit, and that's where these kind of clamshells can be a good fit there to make sure that These are insulated in case they are chilled water. There's actually a separate jacket for this particular product for chilled water. This would be the heating only jacket, but we still have the actuator out there so it doesn't get too hot. So what do we need to commission these different systems? So with a manual balancing valve, we can get our flow chart out and we say we want 3 GPM through this valve. So we need to find on the chart, we have to make sure that we don't mess up which of these valves we're looking at. All these lines can be hard to decipher sometimes. And we need to get a really accurate manometer to say that we've got 3 PSI down to to a hundredth of resolution of pressure drop across this valve may be required to get that dialed into 3 GPM. Can be done if a maintenance person in the building thinks that this is an isolation ball valve and closes all the way down. You have to start over. You have to do that whole building again. And that's kind of the downside of a manual balancing valve, that you'd have to have the balancing contractor come back in and line up all these charts again and go through the whole building again. An automatic balancing valve is a good fit in what I would kind of look at as a speed limit for a particular terminal unit. This is where there's overlap with plumbing too, that on a DHW recirc line, maybe we want to establish a maximum foot per second velocity with a manual balancing valve with PEX connections, and just put that in, that even if somebody down the line changes the circulator, we're not going to be way above the flow rate we're looking for. This is going to be the lowest number of labor hours. With all these different tailpiece options, we can just use PEX cold expansion or crimp or press or whatever and put this in, point it in the right direction. We say that we want 1/2 inch NPT male with a gauge at a 2.6 flow rate in this example, and that's our part number. We just pointed it in the right direction. It's easy. Pressure independent control valves, I'd say a low number of labor hours. There's still a little bit more to do to get this into a system, to wire it, that we didn't have wires with the other 2 valves. That's going to take a little bit more time. Low potential for rework because there is such great adjustability here, that as long as we were in the ballpark with our sizing, that we can say we want a 0.45 GPM and we're okay with a 3.6 PSI drop across that valve. We select this part number here. We put it at position, what did I just describe? Position 5, and then we hook it up to the building management system. So highest energy efficiency potential and best resolution for control there. So those are kind of a few ways to break down the balancing valve selection. And again, there's no wrong answer here, and it depends on what we're looking at as far as the installation cost. If we're looking at the 10-year cost for the energy in a 40-story hotel, the PIC valve can be a really good long-term investment from an energy efficiency standpoint. Depends on who's writing the check and who's paying attention to those different pieces of the system. So I'm going to move on to the last segment here. Let me take one more look at the questions and see if I missed anything that I can go back to here. Some of these I'm gonna have to get back to after the webinar is over. Okay, yeah, the manual balancing valves are most labor intensive and depend on the manufacturer. So fixed speed circulators, as mentioned before, are going to be really harder to tune with a manual balancing valve. It isn't necessary to have a variable speed pump. I think that the ECM pumps are just a good technology because there is that adjustability. One of the things that you would need to check is that for a, I'll go back one slide here. Let's say we're using a PIC valve and are using a single speed pump, but then we're also going to send a 1 volt signal to that the room is up to temperature and start to close down. We could be, if all of the building is warm in a heating example, and all of those proportional controls are telling that PIC valve to close the orifice down to a minimum, we could almost deadhead a pump there. We could ruin a pump if we don't have the ability to slow down enough with the PIC valves. That's kind of a limitation there of the single speed pump, or even when we say variable speed, a variable frequency drive may only go down to 50%, and that might not be low enough as well. So that's where an ECM pump that could almost go down to a 0 flow condition in some examples might be a better fit there, and just kind of matches the spirit of the energy efficiency with a PIC valve would pair well there. So now, one of the things that we look at with the balancing valve is that in some cases, and maybe this is to scale, that the orifice through these balancing valves could be really small. You have a really small, pea-sized orifice through a balancing valve. A copper shaving or a piece of Teflon tape or dirt from the system because the pipe was laying in the yard for a while, or a kid put a marble into the system, or whatever the case is. There are a lot of small orifices in balancing valves to keep clean, to make sure that we're able to adjust the flow to all of these different components correctly. So what are we protecting in a balancing system? A lot of different things. So with a dirt separator and a magnetic separator, we're protecting the heat exchanger of the boiler or the heat pump. That's going to be the most expensive single component, kind of the engine block of the system. We're protecting these new circulators. This is an ECM circulator, as kind of described here. Those three are going to be very expensive components. And also all of the terminal units. So if we plug up a fan coil with a bunch of dirt, we're in trouble there. It may take some labor to try and flush it out, or we may be replacing that entire component in some cases. Radiant's going to be even harder there. If we fill this up with mud, we're going to have a lot of trouble if we can't pump that debris through and purge it out through the valves here and isolate the blue and red here. That's embedded in concrete in a lot of cases. So we really need to be ahead of the schedule and make sure we don't get dirt through that system. Same thing with the balancing valves. If these orifices plug up with a bunch of dirt, we may be trying to balance something that is going to be impossible to find the right number, because it's not just the task of balancing, it's the task of balancing something that the orifice has really been compromised and is filled with dirt. And you'd have to take all those out and clean them and really start over again if that was the case, if you were balancing through a dirty valve. So what are we trying to do here, and what component is best to help us keep a balancing valve clean? So there's a big difference between a filter and a separator. So a filter is something that, like a chain link fence, is going to catch every leaf that blows into the chain link fence. But if you have too many leaves up against that chain link fence, you could blow it over eventually. You've got a lot of pressure that you're creating that the air can't go through those holes in between the wire and get through the fence anymore. That in a hydronic system, if a basket strainer starts to fill up with debris, here's an example of the pressure drop that changes in a clean basket. So from 0 GPM to 16 GPM, we added 1.5 PSI pressure drop. But if that thing is 70% plugged, it's even off of our chart here as far as adding 6 PSI of pressure drop, we don't have the right pump anymore. We would have to either clean out that basket or go back in with a bigger circulator, which we don't want to do either. So that could be a problem. That's kind of one of the inherent limitations to a Y strainer, is that if it's not clean all the time, we've really changed the whole dynamic of our system, and we might have to balance around that or get the dirt out there. So that's where a separator can be a good fit, because the way that a separator works is the dirt goes in, hits some sort of coalescing media, which is just a fancy way to say to gather, and then it falls down out of the flow path. So then the water can keep going through even at a high flow rate without having to fight through all of the debris that was collected, all the leaves that are in the chain link fence there, unless you fill this completely up with garbage, which can happen sometimes, that we fill up a whole system with system debris, and that needs to be purged. But if it's just those kind of installation things that are hard to catch, a solder ball or a little piece of Teflon tape or something like that, those don't obstruct the flow, and then we can have a much more minimal flow penalty going through these devices, even if we've captured a bunch of dirt. The other difference between a Y strainer and a separator is that a Y strainer is going to catch something big, a big chunk of welding residue from a separator or something like that on the first pass. It's going to catch it and it's going to hold it there. With a separator, they are multi-pass devices. So the smallest pieces of grains of sand may, depending on the flow rate, make it through this device the first pass. So that could be something that gets all the way up, in a worst case scenario, into the orifice of a balancing valve, that little grain of sand. However, the upside of the dirt separator is that through those multi-passes, it's going to catch stuff so much smaller than a Y strainer would be able to do. So we could keep going smaller and smaller with the mesh of the Y strainer, kind of the wires and the grid per square inch, but it's going to increase the pressure drop across that basket all the time, where the dirt separator is a nice way to get even really, really, really tiny pieces of sand and rust that would just blow through a Y strainer forever out of the system and separate it down into the bottom. So that's useful. Where do we put these things? So I would say that separators from 3/4 inch for this Dirt Mag Pro, or this Caleffi XF is a new one that actually has both a filter and a collision media. So this is kind of both a basket strainer and a magnet and a dirt separator, so kind of a 3-in-1 device there. These products right here are going to protect the point of distribution. Think of it almost as a mixing valve in a plumbing system. Point of distribution is the biggest pipe coming back to the boiler. So maybe this is a 2-inch or 4-inch or 12-inch separator. This is where we're going to be able to collect a lot of dirt, just an enormous pile of dirt into a big separator like that, that would plug a basket strainer out at the point of use. We'll call the point of use like the fan coil or something like that. If we didn't have any of these point of distribution separators, and we were just trying to get piles and piles of dirt out of an old hotel that's 100 years old or something like that through basket strainers, we're just going to plug these constantly. So this is from the fan coil kit that we actually put the strainer right into the handle to make that really compact and serviceable. But this isn't going to hold a lot of debris. That's going to catch that copper shaving or solder ball or something like that, which is great. Those little grains of sand before they get into the orifice of the pressure independent control piece of the PIC valve. Or we can use a basket strainer like this. But if we're just using those and don't have dirt separation in one central part of the building, we're going to plug these up all the time, and it's going to affect the performance of the building. And what happens in some cases is they fill with dirt, and then people just start changing the circulator, start putting in a bigger circulator to fight through the partially plugged Y strainer that they can't find that was buried or covered in insulation or something like that. So we want the heavy lifting to be done by the point of distribution, by the dirt separator, and we want kind of the last chance to catch something big to be left to the Y strainer or the basket strainer closer to the terminal unit that may be a 3/4 or 1/2 inch size there. That's not going to hold a lot of dirt. It's kind of the last chance to get everything out. So let me wrap up with a couple case studies to kind of show where a PIC valve could be a good fit. So this was a project in Dubai that we worked on. There was a fire during construction. So before the building was occupied, they had a fire and they had to replace a bunch of things in the mechanical system. So they originally had manual balancing valves, and they decided to go with a PIC valve instead. This, if I were just to look at a building on Earth that would be a great fit for a PIC valve, it's going to be something like this: multi-story hotel. This is a premium hotel building. Comfort's going to be a very, very, very high priority for these expensive rooms every night in the condos and things like that. And then also, this is a very hot place on Earth, and having the down to 5% accuracy for the temperature control, it's going to make a huge difference in this building. We have PIC valves in our building in North America, in Wisconsin, in Milwaukee. They're probably a little bit overkill. We put them in because we sell them, and we wanted to make sure that we knew how they worked and that everybody can work on them and we can adjust them. We don't have that many zones. We don't have anywhere near this much of a building. We're very concerned about energy efficiency, so we wanted to make sure we had our own premium balancing valves in our building. Do all warehouses with 35 people in them need PIC valves? Maybe not. This building is an excellent fit for a PIC valve, and this would be where I would look for these kind of superstructures and anything where the energy bills are going to be tens, hundreds, millions of dollars per year. That's an excellent fit for a PIC valve. Another one is this project in Vietnam, where they said the humidity could be close to 100 a lot. Like, this is a jungle environment, and the relative humidity being so high, the dew point is just very hard to work with, and we need to just be as absolutely precise with our temperature control for the chilled water into those spaces as we can. a 3 degree Fahrenheit swing there might be enough to hit a dew point. And that can be a really important thing in that type of scenario as well. Or in just a really big hotel with really sensitive customers who may only be there for a day and want that premium temperature experience. They do not want to have to call down to the front desk and say, it's too cold, it's too hot, it's too loud, the swings are, too much, I don't like hearing the equipment come on and off. That's where we can just really put these PIC valves into cruise control and make sure that we're delivering like down to the BTU, the right amount of energy to these spaces in this, again, warm environment in Vietnam, to make sure that we've got the cooling really dialed in here. So that takes me right to the top of the hour. This is what we talked about today. I'm going to try and catch a couple of the questions that were typed in here and see if I can answer those before the end of the webinar. And if not, I'll get back to you after the webinar is over. Here's our team. If you have any questions about a project, you want to know which of these valves works for a set of plans that's on your desk today, what would be the criteria to go into a little bit more detail based on this specific project, we're always happy to help. One of the things that I love about our team is that we will go into system and application support, even if it's not the specific valve that we sell, because we want to make sure that we've got these things tuned in well, and that may involve some sort of overlap with the circulator or a pump or a heat pump or a terminal unit that we have to kind of figure out how to mend all of these things, how to bring all of them together to make the most energy efficient system. Our team at tech support is just really good at connecting the dots there and not just saying, oh, that's not our valve, that's not our problem. So give them a call. Also tag us on social media if you've got cool projects that you're working on. We love to like and share those and make sure more people see the wins that you're having out in the field. So with that, I'm gonna go to the end of the presentation here and see if I can get to a couple of these questions here. So a lot of, one of the comments is that these PIC valves, most manufacturers have these prepackaged coil connection components. It's a really good way to go. That is going to give you the proper sizing for all those different things for the bypass and the filter. And it is just a great recommendation if you're going to implement a PIC valve to go with the coil kit. That's the most typical application. What is the minimum delta P required for your PIC valves? I don't think I had that chart in enough of a resolution to dig into that, but I'm going to respond to that one by email to follow up. Let's see. So the PIC valve does require a BMS. You're going to need to give that a 0 to 10 DC volt signal or a 4 to 20 milliamp signal, depending on the actuator that you're looking for. But you could use just an on-off 24 volt actuator basically as part of a PIC valve. In a simple example, that may be, depending on the project, not the accuracy that you were looking for. If you really want to dial it in, a BMS with a proportional signal is going to be kind of the premium energy efficiency there. Let's see, why wouldn't you want a Y strainer and a separator? I say both. I think that both is definitely a good way to go, and you don't need 50 different dirt separators throughout the building. Maybe you do one of those big flanged 6-inch steel separators in the mechanical room, and then Y strainers that are no bigger than a 3/4 inch size, just right at the terminal unit, can be a good way to go. Let's see. So the excellent fit because they have the money for that project in Dubai, I think maybe was the comment there. Yeah, kind of. I think that the PIC valve is a good fit for premium. If you want to do premium comfort for someone who's going to pay $700 a night to stay in a hotel room, that can be a good fit for that criteria. It could also be a good fit for a school, because one of the things that I've heard is for most schools, the line items on the balance sheet, the teacher salaries are number one and utilities are number two. So even in a school where there's not a $700 a night hotel, we would rather use that money for books or for something else in the classroom. And those are the scenarios that maybe a PIC valve is a good fit for something that's not premium luxury condos or whatever, but just like we really need to dial in the energy bills, and we're building this school that taxpayers are going to pay for 40 years or 50 years or hopefully more for that type of construction. So There was a question about how to size PIC valves. I can send you a specific document about that that goes into a little bit more detail. And we also have a selection guide on the website that maybe I can toss into the chat quick here. I think that's going to take me to the end of the questions here. A couple of these are more project specific that I'll follow up with, but I wanted to say thank you for sticking with me today. We're a couple minutes over here, but this is a really cool conversation, and I think that there are a lot of energy efficiency problems that we can solve here and keep people comfortable at the same time. So thank you so much. We'll see you next month with Cody and Kevin to talk about thermal balancing. So we'll go to a plumbing version of this conversation and get really into the weeds there. So thank you. Have a good day, and we'll see you soon.